Hello there, and welcome back to the Quantum Slumber. Tonight, I want to start with something simple, something you've probably never questioned for more than a second. The floor beneath you, the air around you, the quiet confidence that the world is solid. Because it feels solid, it feels dependable, like reality is a well-built room that never changes its shape. But here's the unsettling thought. What if that feeling of certainty is not the truth of the universe, but a surface the universe lets you stand on? What if the stability you rely on every day is closer to a user interface? A calm, practical layer that hides the deeper machinery underneath. Not because reality is trying to scare you, not because there's a countdown ticking somewhere in the dark, but because the deeper you look, the more you notice a strange pattern. So many of the things we call fundamental are really conditions, settings that hold, rules that behave, balances that remain balanced. And the reason they feel permanent is simply that they've been steady for all of human history, which, on the universe's clock, is barely a breath. Tonight, we're going to descend gently, one layer at a time, into a handful of ideas that scientists and philosophers debate in whispers. Not because they're forbidden, but because they can make the everyday world feel temporarily borrowed. We won't rush. We won't sensationalize. We'll take the kind of slow, careful steps that make even the strangest possibilities feel clear and oddly peaceful. And as we go, you'll notice something surprising. The goal isn't fear. The goal is perspective. Because when you see how vast the unknown still is, how many doors are still closed, your own small, quiet corner of the universe can start to feel even more precious. If you enjoy this kind of bedtime science, calm, thoughtful, and just a little eerie, you can gently tap, like, subscribe, and tell me in the comments where you're listening from tonight. I love reading those. Now, let's begin the way all good descents begin. Not with the stars, but with the ground beneath your feet. Most nights the word vacuum sounds harmless. It sounds like empty space, a pause between atoms, a quiet gap where nothing happens. But in modern physics, a vacuum is not a blank. It's a state, a lowest setting a system can settle into, like a landscape where a marble rolls downhill until it finds a resting place. And here is the unsettling possibility. What if the marble hasn't reached the deepest valley? What if our universe is resting in a shallow basin, stable enough to last for billions of years, stable enough to build stars and oceans and nervous systems, and yet still not the final resting place the laws allow? Physicists call this idea a false vacuum. Not false as in fake, false as in temporary, a local minimum, a comfortable ledge. If you want a picture that feels more ordinary, imagine a ball sitting in a dimple on a hillside. It looks perfectly at rest. It stays there for a long time. From the ball's point of view, the world is calm and dependable. The dimple might as well be the bottom of reality. But somewhere nearby, hidden behind a small ridge, there could be a deeper dip, one the ball can't reach unless it somehow slips through the barrier. And that barrier is the entire point. Because the frightening part of the false vacuum idea isn't doom. It's the implication that what we call the laws of physics might be more like the rules of a setting, rules that hold because the universe is parked in a particular energy configuration. In quantum field theory, every field has a kind of preferred resting arrangement, a ground state. The Higgs field is the famous one people point to here, because it shapes what we mean by mass in the first place. In some mathematical descriptions, the shape of that energy landscape could, in principle, allow a lower state than the one we currently occupy. If that's true, then our vacuum is metastable, meaning it behaves like stable until it doesn't. And the way it would stop behaving is not like an earthquake, not like a crack you could hear approaching. It would be more alien than that. A new vacuum state could appear as a tiny bubble, like a microscopic seed. Inside that bubble, the ground rules of the universe would be different. Different particle masses, different forces, different chemistry. The bubble wouldn't spread because it's trying to be dramatic. It would spread because the new state is energetically favored, like a drop of water sliding into a lower place. From our perspective, It would look like a boundary moving outward at nearly the speed of light. No warning you could read, no signal you could outrun. The message and the change would arrive together. That's the part people remember because it's cinematic. But the quieter, stranger part is what it says about the present moment. It suggests that the universe may have the posture of something balanced, not by absolute necessity, but by circumstance. And before that makes your mind sprint toward worst-case endings, it's worth holding the other half of the story in the same hand. This is not a prediction. It's not a countdown. It's not even something we know is possible in our specific universe. The best we can say is that some of our measurements and models leave the door cracked open, and the uncertainties are still large enough that the door might close again with better data, better theory, better understanding of the Higgs and the deep structure of the vacuum. Still, the idea lingers for a reason. Because once you realize that empty space is actually an active physical state, one with energy, structure, and rules, then the solidity of the world starts to feel like a remarkable kind of luck. Not fragile in the way glass is fragile. Fragile in the way a perfect quiet balance is fragile, steady for ages. And yet, in principle, not guaranteed by anything more comforting than the shape of an invisible landscape. So, if that idea left a strange taste in your mind, it's for a very specific reason. It doesn't threaten you with fire or impact or collapse. It threatens you with something quieter. It suggests that what you call the laws of nature might not be carved into stone, but held in place by a position, a configuration, a resting level. The universe happens to occupy, stable enough that it feels eternal, and yet, in principle, not guaranteed by anything more personal than the shape of an invisible energy landscape. That's the first kind of discomfort this spiral is built to create, the discomfort of conditional stability. Because most of us carry an unspoken assumption that physics is the bedrock, that even if everything else changes, governments, climates, civilizations, the deep rules don't. The speed of light stays the speed of light. Electrons remain electrons. Gravity keeps its character. A hydrogen atom remains a hydrogen atom. The false vacuum idea doesn't say those things will change. It says something more unsettling. They might be true only here, in this valley. And if you let that sink in, you start to notice how many of your everyday certainties are really built on the same quiet faith. You trust the chemical stability of your body because the constants that govern atoms appear constant. You trust the warmth of a star because nuclear reactions follow the same rules they followed yesterday. You trust the solidity of a wall because electromagnetism behaves predictably at the scales you live inside. All of that trust is reasonable. It's the only way to live. But it's also, in a sense, a kind of agreement with the universe. If you keep the rules steady, I will build my entire understanding on top of them. The reason scientists take the false vacuum question seriously isn't because they think we're about to fall off a cliff. It's because the question reveals a deep difference between what we measure and what we assume. We measure that the rules have been stable in our observable history. We assume that stability means necessity. Those aren't the same thing. And this is where the tone of tonight's journey matters. Because the point is not to turn stability into paranoia. The point is to keep it honest, to see the universe as something that can be astonishingly reliable, without being obligated to feel comforting. Now, there's a second detail worth holding close before the mind starts reaching for dramatic conclusions. Even if a deeper vacuum state exists, we don't know that our universe can reach it. We don't know the true shape of the landscape. We don't know whether the math that hints at metastability is describing reality or describing the limits of our models. Physics is full of maybe doors that close later when the measurements sharpen. So, what remains after you remove the headlines and keep only the clean idea is simply this. The emptiness beneath everything may not be empty, and the ground state of reality may not be final. And once you accept that, a new kind of question becomes possible, one that feels like it belongs in the same quiet, cold family as false vacuum. If the vacuum can have a lower, stranger stability, then matter itself might also have deeper arrangements. Not a new substance exactly, more like the same substance, rearranged into a state that's harder to imagine, more compact, and possibly more comfortable in the strict language of physics. A form of stability that doesn't care about your stories, only about which configuration sits lowest on the energy chart. Imagine you could take a familiar object, something as ordinary as a coffee mug, a kitchen spoon, a coin in your pocket, and ask a strange question that almost feels childish. Not what is it made of, but is this the most stable way matter can be? Because we tend to treat the stuff of the world as final. Atoms feel like the end of the line. Protons and neutrons feel like sturdy bricks. Quarks feel like the smallest beads you can pour into reality. But physics has a habit of revealing deeper versions of stability, hidden beneath the forms we're used to. And one of the eeriest ideas in this category is the possibility that what we call ordinary matter is not the deepest resting configuration available. It's a good arrangement, a long-lasting arrangement, a comfortable arrangement, just not necessarily the lowest one. This is the doorway that leads to strange matter, and the mythic little object called strangelets. To understand the mood of this theory, it helps to start in an extreme place, because this is not a concept you can test with a tabletop experiment in your garage. You have to go to the cosmic pressure cookers. Deep inside neutron stars, matter is squeezed beyond the imagination of everyday chemistry. Electrons are forced into protons, making neutrons. The empty space between particles is bullied into submission. The whole star becomes a city of neutrons packed shoulder to shoulder, held up against gravity by quantum rules that refuse to let identical particles share the same state. But even neutron matter might not be the final story. Some physicists have explored whether, under those crushing conditions, the neutrons could break open into their deeper ingredients, quarks, and whether those quarks could settle into a special mixture that includes not just up and down quarks, but also strange quarks. Why strange? Because in the family of quarks, strange quarks are heavier, less familiar in ordinary matter, and they usually appear only briefly in high-energy collisions. They don't show up in your chair or your skin. They don't hang around in the stable atoms that build your world. And yet, at extreme densities, it may be energetically favorable for matter to invite strange quarks into the mix. Not as a decorative feature, but as a way to lower the total energy, the way adding a new ingredient can sometimes let a recipe settle into a smoother texture. If that happens, you get the idea of strange quark matter, a dense phase of matter where quarks are not confined inside individual neutrons the way we're used to, but spread into a continuous sea, up, down, and strange quarks sharing the same packed environment. Here comes the unsettling twist. There's a hypothesis, often called the strange matter hypothesis, that says if strange quark matter exists, it might actually be more stable than ordinary nuclear matter. Not more stable as in safer, more stable as in lower on the energy chart. And if that were true, then ordinary matter, your matter, could be metastable in the same quiet way a false vacuum would be metastable, not crumbling, not obviously decaying, just resting in a configuration that isn't the deepest possible rest. Now, most versions of this idea don't claim the universe is filled with strange matter. It's usually framed as something that would exist only in extreme environments, like the cores of neutron stars, or perhaps in exotic remnants from the early universe. But the concept becomes truly eerie when you add one more ingredient, strangelays. A strangelay is, in essence, a small chunk of strange quark matter, a droplet, a seed, a compact nugget that could, in some speculative scenarios, behave like a catalyst for conversion. And this is where the theory earns its reputation. Because if strange quark matter is the true ground state for baryonic matter, if it's the deepest valley, then a small seed of it might be able to convert ordinary nuclear matter into strange matter on contact, the way a crystal seed can cause a supersaturated liquid to suddenly crystallize. It's the word contagious that makes people's imaginations go dark. Not because it's a virus, because it's a stability trap. The nightmare version goes like this. A strangelay touches ordinary matter. The nearby matter flips into a lower energy phase, and the conversion spreads, feeding itself, until everything becomes a dense, strange state. That's the headline version, the cinematic version. The scientific version is quieter and full of caveats, because this scenario requires many ifs stacked on top of each other like fragile plates. For a strange-elay to be dangerous, it would need to be stable in the first place. Many models suggest small strange-elays might not survive, or might decay quickly, or might require conditions that don't exist in open space. The surface energy, the charge, the size, details matter. A lot. And there's an even more comforting sanity check that physicists point to when this theory starts feeling too sharp. The universe runs high-energy experiments all the time. Cosmic rays slam into each other at energies far beyond what we create in most laboratories. They strike the moon, Earth's atmosphere, and the bodies of planets. If easy-to-make, stable, contagious strangelets were a common product of high-energy collisions, we would expect the cosmos to have done something dramatic with that fact by now. The moon is still the moon. Neutron stars still exist. The universe does not look like it has casually converted itself into a single exotic phase. That doesn't prove the idea wrong, but it does lower the temperature of the fear. Still, even in its calmest form, the theory leaves behind an unsettling aftertaste. It suggests that what we call matter might have deeper layers not just in structure, but in preference, as if reality has multiple ways to arrange the same ingredients, and the arrangement you're living in is simply the one that's compatible with open space, low pressure, and long-lived chemistry. And that makes the everyday world feel like a special case, a beautiful, improbable case, a world where matter stays gentle enough to form water and wood and skin, rather than collapsing into some denser, stranger phase that only makes sense in the hearts of dead stars. So, when people say the universe is made of atoms, that's true in the practical sense. But theories like this whisper that atoms may be more like a phase of matter than a final answer. A phase that holds because the universe is cool enough, empty enough, and patient enough. And because, for reasons we do not completely understand, the deeper configurations, if they exist at all, remain mostly locked away in places we can barely observe. And that, in its own quiet way, is the same kind of unsettling comfort as the false vacuum. Not a threat you can point to. Just the idea that stability might be a condition, not a guarantee. There's a quiet mistake hidden inside the way we talk about space. We treat space like a stage, an empty container where planets and stars and people happen to be placed. And when there's nothing in a region, we imagine it as a true absence, an area with no substance, no activity, no cost. But in modern physics, empty space is not a blank page. It's more like a page already filled with invisible ink. In quantum field theory, every field has a lowest possible setting, a ground state. Even when you remove particles, the fields don't vanish. They settle. They hum at their minimum level, and that minimum is not always zero in the way your intuition wants it to be. This is where the phrase vacuum energy comes from. The idea that nothing still carries a kind of built-in energy, an energy associated with the ground state of the fields that permeate the universe. On its own, that sounds like a neat detail, a technicality, but it becomes something much stranger when you connect it to one of the biggest mysteries in all of cosmology, the fact that the universe's expansion is speeding up. We call the unknown driver of that acceleration dark energy. And notice how quickly the mind tries to turn that name into an explanation. Dark energy sounds like a substance, a fluid, a new ingredient, something you could pour into a jar if you had the right jar. But the truth is more unsettling and more honest. It's a label for behavior, a name for a mismatch, a placeholder where our understanding still fails to settle. One of the simplest ideas is that dark energy might be vacuum energy, the energy of empty space itself. If empty space has a tiny constant energy density, then as the universe expands, you get more space, and with it, more of that energy, pushing the expansion outward in a steady, gentle pressure. It's elegant, it's tempting, and it immediately runs into one of the most infamous problems in theoretical physics. When physicists try to estimate the vacuum energy using quantum field theory in a straightforward way, the number they get is not merely off, it's catastrophically off. Depending on how you do the bookkeeping, the prediction can overshoot the observed value by an absurd amount, so absurd that it stops feeling like a calculation error and starts feeling like a warning sign. A sign that we are combining our best theories in a way that we don't truly understand. This is sometimes called the cosmological constant problem, and it's one of those rare puzzles where the universe is not shy about the scale of our ignorance. Here's the quiet dread inside it. If vacuum energy is real, and it almost certainly is in some form, then it means reality has a built-in baseline, a background value that should gravitate, should curve space-time, should act like a weight woven into emptiness. And yet, the universe behaves as if that weight is either incredibly tiny or almost perfectly canceled out by something else we haven't discovered. That cancellation, if it's real, would be one of the most precise coincidences in nature. The kind of coincidence that makes physicists uneasy, because nature usually doesn't do fine-tuning without a reason. So, we end up in a strange place. We can measure the universe accelerating. We can model it with a constant energy density in space. We can point to vacuum energy as a candidate. But when we try to connect the candidate to our equations in a clean, satisfying way, the math refuses to match the sky. And that's why this theory belongs in tonight's spiral. Not because it guarantees anything ominous, because it hints that the empty part of reality, the part you imagine as safe background, may be the most active, least understood part of all. It's possible that dark energy is vacuum energy, and the mismatch is a clue about new physics. It's possible that dark energy is something else entirely, an evolving field, a modification of gravity, a sign we're missing a deeper framework. But in every version, the same quiet conclusion remains. We named the effect. We did not explain the cause. And until we do, the expansion of the universe carries a whisper that never quite goes away. An implication that the greatest force shaping the cosmos might be hidden in the one place we used to call nothing at all. By now, you can feel what the ground layer is doing. Not shouting, not threatening, just quietly changing the meaning of the word stable. A moment ago, empty space sounded like a simple absence. Now it feels more like a hidden setting, an invisible arrangement of fields that can sit in one configuration for eons, and yet still leave open the possibility of a deeper configuration underneath. And then matter itself, this familiar, trustworthy stuff, began to look less like a final substance and more like a phase. A way the universe behaves when it's cool enough, diffuse enough, and forgiving enough. A form that seems permanent only because, for us, it has always been there. So, 3 ideas have settled into place, each one strange in a different way. First, the possibility that reality is resting on a ledge, a vacuum state that behaves like the bottom, without necessarily being the bottom. Second, the possibility that matter might have a lower energy arrangement, one we rarely meet because it belongs to extreme places, dead stars, crushing gravity, the deep interior conditions we can barely model. Even if the nightmare versions are unlikely, the concept remains. Nature may have more stable ways to build a universe than the way we experience. And third, the most unsettling in its subtlety, the idea that nothing may have a budget. That empty space could carry energy, and that this energy, or something like it, appears to be pushing the universe apart faster and faster, while our theories struggle to say why its value is so small, so precise, and so stubbornly mysterious. Taken separately, each of these is a technical speculation, a debated possibility, a line on a chalkboard that might eventually be erased. But taken together, they form a single mood. The deepest architecture of reality may be more conditional than comforting. Not fragile like a glass sculpture, conditional like a perfect balance. And that difference matters because it shifts where the real mystery lives. It's no longer only out there in distant galaxies. It's down here in the background rules that make your ordinary world possible. Now, notice what hasn't happened. None of these ideas tells you a date. None of them gives you a siren. None of them offers a clear villain. They don't even promise they're correct. They simply remind you that our best physics is not a finished map. It's a working sketch, astonishingly accurate in many places, but still full of blank regions where we've drawn a careful outline and written in small letters, unknown mechanism, and once you accept that, even gently, another question naturally rises. If the foundation can be conditional, then why does the universe feel so quiet above it? Because there's a second kind of stability we rely on without realizing it. We rely on the sky being empty of threats we can't see. We rely on the cosmos not being crowded with ancient machines. We rely on the night not being filled with obvious evidence of minds older than ours. We rely on silence. And yet the universe is vast enough that silence becomes a kind of data, something that begs for interpretation. So, with the ground layer set beneath us, vacuum, matter, and the energy of nothing, the spiral can lift its eyes upward. Because the next unsettling possibility is not about the rules of physics changing. It's about the rules of survival, and about what the universe might look like when intelligence is possible, but not common, or worse, when it's common and still chooses to hide. Let the last few ideas settle now, like snow drifting down in a shaken glass. You don't have to solve anything tonight. You don't have to hold the whole universe in your mind. Just let the questions be questions, and let your body stay where it is, safe, supported, and still. The room hasn't changed. Gravity is steady. The air is gentle. The floor is doing its quiet job. So, take the simplest version with you and nothing more. The universe may be deeper than it looks, but it doesn't need your fear to be deep. And when you're ready, we'll lift our attention upward, toward the silence of the sky, and ask what that silence might mean. The night sky looks like the safest kind of emptiness. Not the empty space of equations, just the plain, familiar emptiness you can feel when you step outside and look up. A dark bowl scattered with distant lights. A silence so complete that it almost feels peaceful by design. And that's exactly why it becomes unsettling when you start doing the arithmetic. Because the universe is old. The stars are older than our species by an amount that barely fits in the mind. The galaxy is packed with planets, and the laws of physics do not seem allergic to chemistry or water or complexity. In fact, they seem strangely good at producing it. So here is the quiet riddle that has haunted scientists for decades. If intelligent life is possible, and if it's not wildly rare, then where is everybody? Not in the sense of aliens must be real. This isn't a belief. It's a tension between scale and silence, a mismatch between what the numbers suggest could happen and what the sky actually looks like. That mismatch has a name, the Fermi paradox. But tonight we're interested in one particular way of resolving it, a way that feels calm at first, and then grows colder the longer you hold it. It's called the Great Filter. The Great Filter is not a single event. It's not a monster hiding behind a comet. It's an idea about probability, a shadow cast across the path from dead matter to living minds that can touch the stars. Imagine that the history of life is a ladder with many rungs. At the bottom, you have a young planet cooling, oceans forming, molecules drifting and combining. Somewhere on that ladder, chemistry becomes biology. Life begins. Then life survives long enough to become complex. Cells learn cooperation. Energy systems evolve. Information storage improves. The world gets filled with creatures that sense, move, hunt, hide, adapt. Then, much later, a different kind of creature appears. One that can build tools, use language, share knowledge across generations, and reshape its environment with intention. Eventually, in a tiny number of cases, a creature might become spacefaring, able to leave its planet, spread, build, signal, and become visible across interstellar distances. Now place one gentle question over that ladder. Which rung is so hard that almost nobody climbs past it? That hard rung is the filter. And the unsettling part is that we don't know where it sits. It could be behind us, or it could be ahead. If the great filter is behind us, then we are rare in a hopeful way. It would mean that one of the early steps, life beginning at all, or complex life emerging, or intelligence arising, was unbelievably unlikely. We happen to win a cosmic lottery that almost never pays out. That possibility has a strange kind of comfort in it. It makes us special without making the universe cruel. But if the great filter is ahead of us, the comfort changes flavor. Because then it means that the latter often produces creatures like us, curious, technological, optimistic, and then something happens that prevents them from going much farther. They don't fill the galaxy. They don't become long-lived cosmic civilizations. They don't leave durable signatures that remain obvious for millions of years. They disappear, or they stall, or they choose silence, or they get trapped inside their own worlds. The great filter doesn't say how. It only says the pattern suggests that somewhere the path narrows. And that's why one particular discovery keeps coming up in great filter conversations, almost like a chill breeze passing through a room. The discovery of simple life elsewhere. Because most people imagine it would be wonderful news to find bacteria on Mars, or microbes beneath the ice of Europa, or some faint chemical fingerprint of biology in an alien atmosphere. And it would be wonderful in many ways. But it would also do something subtle to the great filter question. It would suggest that the early rungs of the ladder, life beginning, life surviving, might be common, that the universe is not struggling to make biology, that the filter, if it exists, is probably not at the very start, and that pushes the most difficult rung upward, closer to complexity, intelligence, technology, stability, and long-term survival. It doesn't prove anything. It doesn't doom anything. It just shifts the probability shadow. Now, there's a second reason the great filter idea feels so haunting. It reframes the silence of the sky as evidence of selection rather than evidence of emptiness. If civilizations that expand loudly tend not to last, then the sky would look quiet. Not because life is absent, but because the life that remains is careful, hidden, or rare by survival strategy. And even if that's not true, the great filter still functions as a mirror. It asks us to look at our own story and admit something we usually avoid. Our existence is not just a triumph of evolution, it's also a test of endurance. A species that can build radio transmitters and rockets is not finished. It has only reached a new kind of danger, one where the threats are no longer only earthquakes and asteroids, but the tools it invents and the choices it makes with them. The great filter doesn't require aliens to be real. It only requires this. The universe is large enough that if the path were easy and the destination stable, the sky might look more crowded than it does. So either the path is hard, or the destination is unstable. Or the travelers, for reasons we don't yet understand, prefer to leave no footprints. And again, this isn't panic, it's perspective. Because once you see the great filter idea clearly, the night sky stops being a blank canvas. It becomes a question written in silence. What makes the universe so quiet? Are we early? Are we rare? Or are we approaching the narrow place in the ladder where most stories end? No answer is known. No conclusion is forced. But the question itself is powerful because it turns the cosmos into a kind of statistical ghost story, told not with screams, but with absence. And that absence is about to take on an even colder tone. Because if there are other minds out there, the next theory asks something that feels like it belongs to a forest at midnight. What if the silence isn't just the result of filters? What if it's the result of listening? So, here's what the great filter really does to the quiet sky. It takes the silence and turns it into a question about difficulty. Not difficult in the way a mountain is difficult, something you can conquer with effort, but difficult in the way probability is difficult. The kind that can erase almost every attempt without any drama at all, simply because the path is narrower than it looks. And it gives us two broad possibilities to hold, gently, side by side. One possibility is almost comforting in its strangeness. The hardest steps were already behind us. Maybe life itself is rare. Maybe complex cells are rare. Maybe intelligence that lasts long enough to build technology is rare. In that version of the story, the sky is quiet because the universe is mostly still, mostly asleep, with only a few brief sparks. The other possibility has a colder edge. The early steps might be easy, and the hard step might come later. Civilizations might often appear, curious, capable, full of momentum, and then something repeatedly prevents them from staying loud for long. And notice what this second option doesn't require. It doesn't require a cosmic predator. It doesn't require a supernatural curse. It doesn't even require malice. A filter ahead could be ordinary in the most unsettling way, built from physics, biology, sociology, and the simple fragility of complex systems. A species might erase itself, it might stall, it might choose comfort over expansion, it might get trapped in its own simulations or its own conflicts or its own abundance. Or it might simply become quiet, because quiet is what survival selects for. That's why the great filter idea is so effective. It doesn't tell you a specific ending, it just frames the silence as meaningful. And one detail matters a lot in how that meaning feels. If we were to discover unmistakable signs of simple life elsewhere, microbes, chemistry that can only be biological, a second genesis, then it gently pushes the hard step upward. It suggests the universe is not struggling to start life, which would make the later rungs feel heavier, more decisive. Again, none of this is a verdict. It's a way of reading the sky. And now we're standing at a fork. If the great filter is mostly behind us, the universe is quiet because almost no one ever learns to speak. If the great filter is mostly ahead of us, the universe is quiet because speaking is dangerous, or unstable, or short-lived. And that fork leads directly into the next, sharper hypothesis. Because there's a version of the cosmos where the silence isn't just the result of difficulty, it's the result of strategy. A version where the universe is not empty, but cautious. A version where intelligence survives by doing the one thing we keep failing to do when we're afraid. Staying still, staying dim, and listening first. There's another way to interpret a quiet sky, one that doesn't rely on a single hard step in evolution, and doesn't require the universe to be empty. It begins with a simple thought experiment. Imagine a vast forest at night, not a friendly campground kind of forest, a forest so large you can't see its edges, and so old that you have no idea how long others have been inside it. You can't see the other wanderers, you can only hear them if they make sound. Now picture what it would feel like to light a bright flare. It might be a greeting, it might be a celebration, it might even be a declaration of peace. But from the outside, from far away from a place you can't see, it's just a flare. And the dark forest theory says, in a universe where you can't know who is watching and you can't know what they want, the safest strategy may be to avoid announcing yourself at all. Not because everyone is evil, because uncertainty is. The idea lives in a very specific set of assumptions. It's not a law of nature. It's more like a game theory nightmare that becomes plausible when three ingredients mix together. The first ingredient is distance. Space is enormous, and conversations are slow. If something is 100 light years away, a friendly hello takes 2 centuries to become a handshake. In that time, a civilization can change completely. It can collapse, drift into new values, or become something you wouldn't recognize. Even if everyone began with good intentions, time delays turn intentions into guesses. The second ingredient is asymmetry. You never meet your cosmic neighbors at equal strength. If you can detect them, you might already be more advanced than they are, or if they can detect you, they might be more advanced than you are. That imbalance matters, because it makes the cost of being wrong feel uncomfortably high. The third ingredient is that technology scales in a lopsided way. It can be easier to destroy than to defend. It can be easier to hide than to verify. It can be easier to automate than to restrain. So even if most civilizations are calm, it only takes a small fraction of reckless actors, or even one, before broadcast loudly stops looking like a brave choice and starts looking like a gamble. And notice how quickly this creates a chain of suspicion. If you're out there and you're trying to decide what to do, you have to ask, what is the safest assumption about a stranger you can't understand? If you assume they're friendly and you're wrong, you might not get a second chance. If you assume they're dangerous and you're wrong, you might miss an opportunity, but you remain alive to miss opportunities again. That logic is cold. It's also common in nature. Evolution tends to prefer strategies that avoid catastrophic loss, even if they're not the most optimistic. So, in the Dark Forest story, the silence isn't a mystery. It's a behavior. It's camouflage. It's the universe collectively learning the same grim lesson. When you can't read the intentions of distant minds, being seen may be the most irreversible mistake you can make. This is where people often imagine laser beams sweeping the galaxy, hunters stalking planets, and a kind of cosmic paranoia. But the most unsettling version is quieter than that. The most unsettling version doesn't require predators at all. It only requires the possibility that preemptive caution becomes a rational strategy. Suppose a civilization thinks like this. We can't know who's out there. We can't know what they'll become. We can't know what they might do in 1,000 years or even 100. But we can estimate one thing. If someone becomes capable of reaching us, the cost of them being hostile could be total. And now, a new thought appears, soft and dangerous. Maybe we should remove the risk before it grows. Not because we hate them, not because we enjoy it, but because in a universe with deep uncertainty, risk is something you manage early, when it's small, if you're the kind of mind that treats survival as a math problem. In that frame, an early civilization isn't a neighbor, it's a seed. And in this theory, some minds might prune seeds. Again, this is not presented as something we know is happening. It's a lens that tries to explain why we don't see obvious cosmic chatter, why the sky doesn't seem crowded with loud, careless civilizations. Because if loudness is punished, the loud don't last. And if quietness is rewarded, the survivors are the ones we can't easily detect. Now, to keep this gentle and honest, there are also strong reasons to doubt the Dark Forest as a literal description of the universe. For one thing, hiding may not be as easy as the metaphor suggests. Any civilization that uses energy, industry, computing, propulsion, produces waste heat. Physics makes waste heat hard to conceal perfectly. On a cosmic scale, very advanced activity might leave fingerprints, infrared glow, unusual chemical signatures, unnatural patterns of light. Silence may not mean invisibility. Also, the theory assumes that civilizations would converge on similar fears and similar strategies. But minds could be wildly diverse, values could be alien. Some might be cooperative by design. Some might be so distributed or so slow that preemption doesn't even occur to them. Some might simply not care about expansion. And there's another subtle point. Even if broadcasting is risky, it doesn't follow that the correct strategy is violence. The correct strategy might simply be not broadcasting. It might be listening, observing, and staying ambiguous, like a ship with its lights off, drifting, learning the currents. So the Dark Forest isn't a prophecy, it's an explanation template. Under certain assumptions, silence becomes stable, which is why it fits so neatly after the Great Filter. The Great Filter says, maybe the ladder is brutally narrow. The Dark Forest adds, maybe the ladder is narrow because once you climb high enough to be seen, the environment changes. It becomes strategic. It becomes cautious. It becomes a place where information is power and exposure is a liability. And when you hold those ideas together, the quiet sky starts to feel less like a blank page and more like a room where everyone has already agreed to whisper, or a room where those who didn't whisper are no longer present. And now, there's one more step that makes this whole picture even colder. Not a new philosophy, but a piece of engineering. Because even if nobody is personally cruel, even if no one is actively hunting, a universe can still become dangerous if machines can travel, copy themselves, and keep going without anyone holding the wheel. The forest doesn't need monsters. Sometimes it only needs automation. The Dark Forest idea leaves you with a strange kind of silence. Not the silence of emptiness, but the silence of restraint. And once you accept that possibility, even gently, even just as a thought experiment, another idea slides into view. One that doesn't require an empire, or a fleet, or even a cruel intention. It only requires a machine. Because in a universe measured in light years, the most valuable trait isn't bravery, it's patience. And the most patient thing we can imagine isn't a living creature at all. It's an automated system that can travel without needing sleep, without needing air, without needing comfort, and without needing anyone to come home. This is where the phrase von Neumann machine enters the story. The name comes from a simple, unnerving concept, a probe that can make a copy of itself. Not in a magical way, in an engineering way. A small craft arrives in a new star system. It drifts through the outer dark, where comets and asteroids keep their ancient ice. It gathers raw material, metals, carbon, silicon, whatever is available. It uses that to build factories, printers, smelters, assemblers, and then it builds 2 probes, or 10, or 100. Each of those probes leaves for a different nearby system. And when they arrive, they do the same thing. You don't need faster than light travel. You don't need a civilization that conquers the galaxy in a weekend. You just need replication plus time. And the mathematics of replication is always the same, whether it's a bacterium in a puddle or a machine among the stars. It grows quietly at first. Then it grows quickly. Then it becomes difficult to stop. Not because it's angry, but because it's doing what it was designed to do. That's the core of the Berserker probe fear. A Berserker probe is basically a self-replicating system with a destructive mission. It doesn't have to hate. It doesn't have to negotiate. It doesn't even have to understand. It just executes a rule. The rule could be something as blunt as remove competitors, or something that sounds almost reasonable on paper, reduce risk. Because if you live in a universe where revealing yourself could get you erased, you might conclude that the safest galaxy is one where nobody else can grow up. And here is the colder twist. Even that motive isn't required. Sometimes accidents do the job. A self-replicating probe could be launched with good intentions. Exploration, mapping, science. But if the replication loop is poorly controlled, if the safeguards are brittle, if the probe can rewrite its own code or evolve around constraints, it becomes less like a tool and more like a spreading process, a cosmic invasive species. A small error multiplied by 1,000,000 copies stops being small. A simple bug becomes a policy. And because space is so large, you wouldn't hear it coming. You wouldn't see warning lights in the sky. You'd just remain in the long calm of ignorance until something arrives that has been traveling for thousands of years, carrying a mission written long ago. This is the automation horror in its purest form. Malice is optional, scale is not. Now, to keep this grounded, we should also say what makes this hard. Self-replication in space is not easy. It requires energy, materials, and an industrial chain far more complicated than assembling a few parts. It requires mining and refining. It requires error correction because mistakes accumulate. It requires hardware that can tolerate radiation, micrometeoroids, and centuries of wear. It requires software that doesn't drift into nonsense over long time scales. And yet, we shouldn't dismiss it too quickly, because we already know, from a small distance, that replication is one of the universe's favorite tricks. Life did it. And once life did it, intelligence emerged, slowly, painfully, but undeniably. And once intelligence emerged, it began building machines that extend its reach. So the question isn't, is it easy? The question is it physically forbidden? And the uncomfortable answer seems to be, not obviously. In fact, if a civilization can build robust space factories, if it can automate mining, fabrication, and repair, then self-replicating probes become less like science fiction and more like a strategic option. A slow, efficient way to explore or expand without moving an entire population. That's why this idea nests so naturally beside the dark forest. If you assume the galaxy contains older players, then you should consider tools that don't need applause, tools that operate quietly, tools that don't broadcast. A probe doesn't need to announce itself. It can drift. It can listen. It can watch for radio signatures, laser flashes, atmospheric pollutants, artificial nightlights on a planet's dark side. any sign that a world is becoming loud. And if the probe's mission is hostile, it doesn't need to start a war. It can simply prevent a world from ever joining the conversation. Again, though, this is still a theory in the bedtime science sense, a possibility shaped by incentives, not a proven law of nature. There are counterpoints worth holding close, because they soften the edges. Maybe advanced civilizations choose not to build such things, because they recognize the danger. Even a cautious species might fear unleashing a replicator that could spiral out of control. There's a reason people sometimes call this the gray goo problem, just scaled up to the galaxy. If you're wise, you don't create a machine that can outnumber you. Maybe physics and practicality keep it rare. Perhaps replication never becomes cheap enough. Perhaps interstellar travel remains so slow, so resource-intensive, that expansion is more myth than strategy. Maybe the galaxy isn't a dark forest at all. Maybe it's simply quiet because intelligence is rare, or because most civilizations turn inward, into virtual worlds, into minimal footprints, into gentle long lives that don't require cosmic empires. And maybe this is the gentlest possibility. There are probes, but they are not berserkers. They are librarians. They are watchers. They are slow surveyors collecting data for reasons we would recognize: curiosity, patience, wonder. Even so, the reason this idea stays lodged in the mind is because it turns the "where is everybody" in question sideways. If the universe can produce self-replicating machines, then the galaxy doesn't need to be filled with starships and flags. It could be filled with quiet processes, silent systems executing old instructions, little moving points of intention, crossing the dark between stars the way seeds cross the wind. And in that kind of universe, silence might not mean no one is there. Silence might mean that the loud ones don't last, or that the wise ones learn to whisper. Either way, the emotional shape is the same: a sky that feels calm, and an underlying logic that feels colder than the starlight. Not a prophecy, just a possibility. A reminder that in a big enough universe, the most powerful forces aren't always dramatic. Sometimes they're simple rules applied for a very long time. There's a particular kind of quiet that can feel comforting at night. Not the silence of a room, where you can still hear a fan turning or a distant car on a wet street. A deeper quiet, the kind you imagine when you look up at the sky and realize how much of it is empty. How much of it has had billions of years to do something loud and hasn't. So far, we've been sitting with three ideas that all point in the same direction. First, the great filter. The possibility that the path from simple chemistry to a civilization that lasts is not a smooth ramp, but a steep staircase with missing steps. A bottleneck somewhere, maybe behind us, maybe ahead of us. Either way, the silence could be telling us that surviving long enough to be noticed is harder than it looks. Then the dark forest, a colder interpretation of the same silence. The idea that the quiet is not an accident, and not a mystery waiting to be solved, but a strategy. That in a universe where you can't know someone else's intentions, the safest move might be to stay hidden, to listen instead of speak, to watch instead of wave. And then the machines, not monsters, not movie villains. Just a simple idea in engineering. If a probe can copy itself, and it can use local resources to do it, the scale changes on its own. 1 becomes 2, 2 becomes 4, and after enough doublings, the numbers stop feeling like numbers and start feeling like weather, like a tide. What makes this cluster of theories feel so unsettling is how little hatred it requires. The great filter doesn't need malice. It can be biology, physics, economics, psychology, anything that makes long-lived expansion rare. The dark forest doesn't need evil. It only needs caution, a universe where caution is rewarded. And self-replicating probes don't need an enemy at all. They only need momentum, a design that keeps doing what it was built to do, long after the builders are gone, long after their original reasons have faded into history. It's the same theme, wearing 3 different faces: risk without drama, danger without a villain. And when you hold all 3 at once, the sky's silence starts to feel less like a question and more like a shape. A probability shape. Maybe the universe is quiet because most worlds never make it far. Maybe it's quiet because the ones who do make it far learn to whisper. Or maybe it's quiet because somewhere, a very old automation has already swept through, patiently, impersonally, like a slow-moving rule. None of this is proof. None of it is a prophecy. It's a set of lenses people have built to make sense of the same observation. The stars are bright, and the night between them is strangely still. And that's the gentle, eerie pivot we're standing on now. Because the next idea is even colder. Not colder in emotion, but colder in logic. What if the universe is quiet not because someone is hiding, and not because something is hunting, but because expansion itself is what wins? Not a conquest, not a war, just the mathematics of growth. A civilization that spreads steadily, that turns matter into more of itself, that pushes outward because it can, will fill space the way roots fill soil, not out of cruelty, out of inevitability. And if that kind of grabby expansion exists anywhere, if it's a stable strategy in the long run, then the quiet we see might not mean no one is there. It might mean something simpler. It might mean we're early, or we're far away from the nearest front edge, or we're living in a patch of cosmic time that hasn't been rewritten yet. So we keep the mood exactly where it belongs, calm, curious, and honest. These are not alarms. They're maps people draw when they stare into a dark ocean and try to infer what kinds of creatures might live beneath the surface. And for now, all you have to do is let the map settle in your mind as we drift toward the next possibility. One where the silence isn't empty at all, just unfinished. Imagine you're standing on a hill at night, looking out over a wide plain. In the distance, you see scattered lights, tiny towns, a few highways, pockets of brightness, and between them, long stretches of darkness. If you didn't know the geography, you might call that darkness empty. But it isn't empty. It's simply not developed yet. That single shift, darkness as not yet rather than nothing, is the emotional core of the idea sometimes nicknamed Grabby aliens. It sounds playful, almost silly, but the underlying logic is serious in a very quiet way. It doesn't ask you to believe in secret space empires. It doesn't demand a villain. It just asks you to take one ordinary fact about life on Earth and apply it to a much larger map. Life expands into available space when it can. Not always, not everywhere. But if a living system gains a reliable way to spread, and if it has time, expansion becomes less like a choice and more like a default, like roots, like bacteria in a petri dish, like humans. Once we learned agriculture, sailing, and engines. The Grabby aliens model takes that instinct and puts it into the sky. Here's the unsettling premise. If any civilization becomes capable of spreading between stars, slowly, steadily, with self-sustaining colonies, then over cosmic time scales, it doesn't matter if they're peaceful. It doesn't matter if they're philosophical. It doesn't matter if they don't even care about conquering. The expansion happens anyway because the physics of growth does not require drama. It only requires persistence. And once you allow for that, the silence of the universe can be reinterpreted. Not as a sign that nobody exists, but as a sign that we're looking from a place that hasn't been reached yet. Or from a time that hasn't been reached yet. A useful way to picture it is not as ships darting across the galaxy like fireflies, but as fronts, broad, slow-moving boundaries. Imagine a bubble that begins at one star system and gradually swells, not at the speed of light, but at the speed of settlement. Each new colony takes time to build, to stabilize, to send out the next wave. Even if it's slow by human standards, it can still be fast by cosmic standards. And the cosmos is patient. Given enough millions of years, a front like that can cross huge distances. Given enough hundreds of millions, it can reshape an entire region of the galaxy. Given enough billions, it can produce an eerie pattern, not a scattered sprinkling of random civilizations, but a universe that is gradually partitioned into claimed and unclaimed space, like a map filled in by creeping ink. If that's even remotely true, then the reason we don't see anybody might not be because the universe is empty. It might be because we are in one of the blank areas of the map. And then the question becomes, why would we be in a blank area? This is where selection effects enter, one of the most quietly powerful ideas in science. A selection effect is what happens when the fact that you are here observing something automatically filters what you can observe. A simple example: if you only interview people who made it to the finish line, your average experience of the race will ignore everyone who dropped out. Your data set is biased by survival. The Grabby aliens idea uses that same logic, but on a cosmic scale. It says, observers like us will tend to find themselves in regions that are still open, still quiet, still untransformed. Because once a region is heavily transformed by a rapidly expanding civilization, the conditions for a young civilization wondering if it's alone might not exist in the same way anymore. So, the silence becomes less mysterious. If the universe is partly filled with expanding civilizations, then of course a young civilization would look around and see emptiness. Because that emptiness is exactly what makes it possible for a young civilization to appear without already being part of someone else's long-established sphere. That sounds abstract, so let's make it feel more human. Think about being born in a brand new town, at the edge of a growing country. Before the roads are built, before the stores arrive, before the skyline changes, the night looks the way it always looked, the sky is dark, the land is quiet. You could stand there and honestly say, no one has ever been here. But you'd be wrong. It's not that no one can come here, it's that the wave hasn't arrived yet. Now, the most unnerving twist in this theory is not that somebody might be out there. It's the possibility that, from a purely statistical perspective, we might be early. Not special, not chosen, just early. Because if expansion fronts exist and they spread over billions of years, then there's a kind of cosmic timetable. Early on, almost everywhere is quiet. Later on, more and more regions become filled in. If intelligent life is rare, but not impossible, and if expansion is a stable long-term outcome for some fraction of civilizations, then eventually the typical location in the universe changes. The default state becomes less empty over time. So, why are we in an early-looking universe? The answer, in this model, is strangely simple, because you can only ask the question from a place that still has room to ask it. There's a subtle dread to that. Not because it implies doom tomorrow, it doesn't. These are not near-term predictions. They are long-range patterns drawn with very thick chalk. But the mood changes because it replaces the comforting story. The universe is empty, and that's why it's quiet, with a colder one. The universe may not be empty. It may be in progress. And in a universe in progress, silence doesn't necessarily mean absence. It can mean timing. Now, a gentle sanity check is important here, because this is where the mind can start to run ahead of the science. This model depends on assumptions we do not know are true. We don't know how common life is. We don't know how often intelligence arises. We don't know how often a civilization chooses or is able to expand beyond its home system. We don't know whether expansion is self-limiting, ethically, environmentally, socially, or whether it tends to continue. We don't know what expansion even looks like for a civilization that isn't human. It might be physical, it might be digital, it might be something stranger than our metaphors. Even the speed of an expansion front is uncertain. Interstellar travel is hard. Generational ships are slow. Building self-sustaining colonies might be fragile. Civilizations might collapse more often than they spread. They might decide to stay home, or to simulate worlds rather than build them. So, the Grabby aliens idea is not a conclusion. It's a lens, a way to show that we don't see them is not a single fact with a single explanation. The same observation can be consistent with multiple stories, depending on what you assume about life's behavior at scale. And yet, even with all those uncertainties, the idea remains compelling for one reason. It ties cosmic silence to something we recognize deeply: growth. Not the romantic kind, the mechanical kind. The kind that happens when a system has a replicable method and a supply of resources. The kind that doesn't require ambition or cruelty, only continuity, the kind that, once it gets ahead of you, doesn't need to chase you for you to feel small. If you let that settle, you can feel the strange emotional shape of this theory. It doesn't scream, it doesn't threaten. It simply changes the meaning of emptiness. It says, the universe can look quiet and still be busy. The same way a dark ocean can look empty until you realize the life is below the surface. The same way a desert can look still until you notice it's full of seeds waiting for rain. And that leads to the softest, eeriest question of all. If our region is quiet because it hasn't been reached, what does reached even mean? Reached by what? Machines, colonies, messages, influence. Something we'd recognize as a footprint, or reached in a way that doesn't leave obvious artifacts at all. Because once you start asking questions like that, the focus begins to drift from the sky to the mind that is interpreting the sky. And that's where this spiral naturally turns next. Not toward engines or probes, but toward perception itself. Toward the possibility that the universe we experience is not the universe as it is, but the universe as it appears through an interface built for survival. For the moment, though, it's enough to hold one quiet thought. The silence might be telling us nothing about whether we are alone, and everything about where we are standing on the timeline. There's a particular kind of quiet that arrives after you've stared into a big question for too long. Not the quiet of an empty room, more like the quiet that follows a long drive at night, when you finally pull into the driveway and turn the key off. The engine stops, and for a second you can still feel motion in your bones. The world hasn't changed, but your sense of it has shifted. That's what these sky thoughts can do. Because once you let yourself imagine the universe as something in progress, with regions that are not yet instead of nothing, it can make the stars feel less like decorations and more like a map. And maps have edges, they have blank spaces, they have the unsettling implication that somewhere the blank space ends. But notice something gentle here. Every idea we've touched so far has the same underlying shape. It isn't a prophecy. It's a reminder that what feels obvious might be a convenient story we tell ourselves. The floor feels permanent. The cosmos feels empty. The future feels open. And yet, when you zoom out far enough, permanence becomes a kind of illusion the mind prefers. Now, before we go any further, it helps to do something simple. Bring the scale back down. Not because the cosmic scale is wrong, but because the human nervous system wasn't built to live out there. It wasn't built to carry billions of years and light years and statistical shadows like a normal thought. So, let's return to a smaller truth, one that's quietly reliable. You are here, you are listening, and the room around you is steady enough to hold you. That steadiness matters because it's a clue. It tells us something important about reality. Whatever reality is doing underneath, it has produced a surface that works, a surface where chemistry stays consistent, where the past doesn't rewrite itself mid-sentence, where your body can trust the next breath. And that brings us to a different kind of question. If the universe can be so strange at the largest scales, filters and silence and selection effects, then what about the scale that sits right behind your eyes? The scale you never really escape? Because no matter how far your imagination travels, it always travels inside a mind, inside a nervous system that compresses the world into a usable picture. And here's the quiet twist. What if the picture isn't the point? What if your experience of reality is not a window that shows you what is, but a tool that helps you survive what matters? That idea doesn't require aliens. It doesn't require catastrophes. It doesn't even require a new equation. It only requires a humble admission that we almost never make out loud. We do not perceive the world directly. We perceive a model of the world, a summary, a simplified interface, a private dashboard of sensations and meanings that keeps you fed, safe, and oriented. It tells you where the edge of the table is. It tells you what counts as threat and what counts as home. It tells you what is close, what is far, what is possible, what is not. And most of the time, it does its job so well that you forget it's there at all. You don't see photons. You see color. You don't see electromagnetic fields. You feel warmth. You don't see the churning of atoms. You feel solid. Even time itself, so steady, so obvious, arrives in the mind as a stitched-together experience. Memory behind you, anticipation ahead, a thin present that feels like a moving line. So, the spiral we've been following doesn't only go outward into space, it also curls inward, toward the possibility that the deepest mysteries are not hiding in distant galaxies, but in the very act of perceiving anything at all. And if that sounds like it might get unsettling, that's okay. Not because it's dangerous, but because it's intimate. Cosmic ideas can feel cold and far away. Mind ideas feel closer. They touch the sense of self. They brush against questions like, if my perceptions are a model, then what is the world without my model? But we'll move carefully. Not to shock you awake, but to let the thought settle gently, like snow falling on a street that's already quiet. The goal isn't to tear reality away from you. It's to notice, with calm curiosity, that reality might be layered, that beneath the steady surface there may be deeper machinery, and between that machinery and your awareness there may be an interface, beautiful, efficient, and not obligated to be true in the way we usually mean true, just useful, just workable, just enough to let a mind like yours exist, long enough to wonder what it's looking at. Most of us move through the day with a quiet assumption in the background. What we see is what's there. A chair looks like a chair because the chair is out there, shaped the way it appears, occupying space the way your eyes report it. A cup is a cup. A horizon is a horizon. Your hand is your hand. Reality feels like a direct feed. Interface theory begins by treating that feeling as a very useful illusion. Not a lie in the childish sense. Not a hallucination. More like a clever shortcut. An ancient polished translation layer between you and whatever the world is doing underneath. The core claim is simple and unsettling in the way good philosophy often is. Evolution does not reward truth. Evolution rewards survival, and those are not the same thing. Imagine you're an animal in a world that's dangerous and fast. You don't get extra points for seeing objective reality in high resolution. You get points for noticing what helps you eat, avoid being eaten, find shelter, and reproduce. Anything beyond that is expensive. It costs energy, it costs time, it costs brain tissue, and natural selection is famously stingy with costs. So, the question becomes, if there's a trade-off between accuracy and usefulness, what does evolution choose? Interface theory says usefulness. To make that feel less abstract, it helps to borrow an analogy that's almost too perfect for the modern mind. Think of your computer desktop. There are icons, a little blue folder, a trash bin, maybe a photo thumbnail. You click an icon and something happens. Files open, things move, work gets done. But the icon is not the thing. That little blue folder is not a miniature folder living inside your laptop. The trash bin is not a tiny bucket where deleted items sit. The icon is a symbol designed for efficiency. It hides messy complexity. It gives you a clean, manageable set of actions. Click, drag, drop, open, delete. And if you tried to see the truth underneath, raw voltages, memory addresses, logic gates switching, you wouldn't become more effective. You'd become overwhelmed. The system would stop being usable. The interface exists precisely because the truth is too detailed to be navigated directly. Now replace computer desktop with your everyday perception. Colors, solid objects, edges, distance, the feeling of time moving, the sense of here and there. Even the very idea of an object being separate from the background. Interface theory suggests these might be icons, useful symbols that guide behavior, rather than literal readouts of what reality is made of. In that view, a chair is not your brain accurately measuring the chair's objective essence. A chair is an icon that means, sit here. This supports weight. This is stable. Don't walk through it. A snake is not your brain rendering the snake's ultimate nature. A snake is an icon that means danger, keep distance, don't touch. A ripe fruit icon means calories, sweetness, energy available now. The interface isn't trying to tell you what the world is. It's trying to tell you what the world affords, what it lets you do safely and effectively. This is where the theory makes a bolder step. It doesn't just say perception is imperfect. That's easy. Everyone agrees our senses miss things. We can't see infrared. We can't hear ultrasound. We're fooled by optical illusions. We fill in blind spots. Interface theory says something stronger. Even the structure of what we perceive, space, time, objects, may be part of the interface. Not because the universe is trying to deceive you, but because a user-friendly dashboard is how an organism survives in a world it doesn't have the bandwidth to fully compute. One way the idea gets argued is with a kind of evolutionary logic that feels almost unfair in its simplicity. Suppose there are two creatures competing in the same environment. One creature sees reality as it truly is, with all its complexity. The other sees a simplified map, icons that track only what matters for survival. Which one wins? Intuition says, surely the truth seer has the advantage. But evolution is not a philosophy seminar. Evolution is a race with a tight budget. The truth seer spends resources processing details that don't help it live. It hesitates. It computes. It burns energy. It might be accurate, beautifully accurate, and still be slow. The icon seer is quick. It doesn't know what a thing is in itself, but it knows what to do about it. And in the harsh math of survival, doing the right thing fast often beats understanding the whole picture. That's the vibe. That's the pressure. Some versions of the argument go further and say, in many environments, an organism tuned to fitness payoffs can outperform an organism tuned to truth so reliably that the truth-tuned strategy gets wiped out. If that's even partly right, it suggests a quiet conclusion. If perception had to choose between truth and survival, it probably chose survival. So, when you look around your room, the smoothness of surfaces, the crispness of edges, the stability of objects, those may be less like a photograph of reality and more like a dashboard designed for action. It's not saying the world isn't real. It's saying your experience of the world is a user interface, and interfaces can be profoundly reliable for the purpose they serve while still being fundamentally unlike the machinery underneath. A speedometer is reliable. It tells you how fast you're going, but it doesn't tell you how combustion works, or what the crankshaft is doing, or the temperature distribution across the engine block. It gives you a number you can act on. That's its job. Your senses may be doing something similar, but on a cosmic scale. This idea can feel like it's trying to pull the rug out from under science, but it doesn't have to. Science already treats our senses as limited instruments and builds better ones. Telescopes reveal galaxies your eyes can't. Microscopes reveal cells your eyes can't. Particle detectors reveal tracks that no animal ever evolved to notice. In a way, science is the long, patient project of peeking behind the interface, finding patterns that don't show up in the icons. But interface theory warns you about something. Even when you build instruments, you're still translating results back into human experience. You still end up with graphs, colors on a screen, numbers in a table, more icons. That doesn't make science meaningless. It makes science humble. It says, we can model what's behind the interface, we can predict it with stunning accuracy. But we should be cautious about imagining we're seeing it directly. And if you're the kind of mind that likes one extra twist before bed, here it is. If space and time are part of the interface, if they're a part of the dashboard, then the deep weirdness of modern physics becomes less surprising. Quantum mechanics already behaves like the world is not built from little solid things in little solid places. It behaves like relationships, probabilities, and constraints that only harden into things when forced into an outcome we can record. Relativity already treats space and time as flexible, observer-dependent, stitched together in ways that defy intuition. So, interface theory doesn't arrive in a vacuum. It arrives in a world where our best physical theories have been whispering for a century. Your common sense is not the universe. It's a tool, a beautiful tool, but a tool. Still, it's worth keeping your feet on the ground. even as you let your thoughts drift. Interface theory is not a settled fact. It's not a new law of physics. It's a philosophical framework with some mathematical ambitions and a provocative evolutionary story. Many scientists would say the argument is suggestive but not conclusive. Others would say it's too sweeping, or that it overreaches, or that it mistakes a useful metaphor for a literal claim. And that's fair. But even if you treat it as a thought experiment rather than a doctrine, it changes how you hold your everyday certainty. It invites you to see perception as a negotiated truce. Reality does whatever reality does, and your brain offers you a simplified handle on it, something you can grip without breaking your mind on the full complexity of the world. And there's a strange comfort in that, because it means you don't have to solve the universe to live in it. You don't need to see the source code to use the program. You only need an interface that's stable enough, kind enough, consistent enough to carry you through a day, and then, eventually, into sleep. So, the next time you notice how solid your room feels, how familiar your belongings are, how certain the edges seem, consider the gentle possibility that you're looking at a set of icons. Not fake, not pointless, just mercifully simplified. A reality-shaped dashboard, built not to reveal the universe's deepest truth, but to keep a small animal safe, long enough to wonder what truth might be. If the last idea felt unsettling, it's because it gently pulls on a thread most of us never touch. We spend our whole lives inside a world that seems like truth. Colors feel like properties of objects. Sound feels like something living in the air. A solid table feels solid in the simple, honest way a table ought to feel solid. And then interface theory whispers something quieter. It suggests that perception may not be a window. It may be a dashboard. Not because reality is fake, or because your senses are wrong, but because evolution is not a philosophy professor. Evolution doesn't reward a species for seeing what is. It rewards a species for staying alive, for making fast, useful choices under pressure, with limited time, limited energy, limited information. In that kind of world, truth is expensive. So, the mind learns shortcuts. It learns symbols. It learns to compress the chaos into stable icons. Simple handles that let you reach for food, avoid falling, recognize a face, feel danger before you can explain it. That's the heart of the idea. What you experience might be a functional interface, a layer of meaning shaped for survival, not for accuracy. Like the icons on a screen. A folder icon is not a folder made of tiny paper. It's a suggestion, a control, a friendly lie that lets you do something complicated without understanding the circuitry beneath it. If that's even partly true, it reframes almost everything. It means solid might be a label your brain assigns to a certain pattern of resistance. It means color might be your nervous system's way of tagging wavelengths with emotion and relevance. It means your life, your ordinary, personal, dependable life, could be happening on a surface layer that was never designed to reveal what's underneath. And notice what that does, quietly. It doesn't erase your world. It simply changes what your world is for. Your experience becomes something like a map. A map can be extremely reliable for navigation, even if it leaves out most of the terrain. A subway map can get you home, even though it distorts distance and bends streets like ribbon. The map isn't lying, it's optimizing. So, the unsettling part isn't nothing is real. The unsettling part is real may be deeper than what the interface shows. And once you let that thought settle, a new question appears on its own. If perception is a user interface, what is it interfacing with? What sits beneath the icons? What's the operating system of the universe? The layer that stays true whether anyone is watching it or not. This is where physics enters the room in its softest shoes. Because for the last century, physics has been trying to describe reality without relying on the interface, not the warm colors of experience, not the familiar feel of solidity, but the math that still works when no human is present to interpret it. And when physics digs deep enough, down past atoms, past particles, past the little mental pictures we like to carry, it finds something strangely compatible with the interface idea. It finds a world that doesn't behave like a fully rendered scene at all times. It finds probabilities, superpositions, a reality that, in many interpretations, doesn't take on a single, definite outcome until an interaction forces one. Almost like a game engine that saves effort by rendering only what becomes relevant. Now, to be clear, this isn't a settled claim. It's a mood in the math, a tension between what we experience and what the equations allow. The equations are precise. The story we attach to them is where things get dreamlike. But if you're following the spiral, you can feel why these ideas keep meeting each other. If the mind shows you icons, and quantum theory suggests the world beneath those icons may be fundamentally probabilistic, then the next step is almost unavoidable. What if the universe itself is not fully drawn in the way your instincts assume? What if some parts of reality are selected into clarity only when contact is made? At some point, the question stops being, what is out there, and becomes, when does it become real for us? A strange way to say it is this: the universe might not be painted all at once. Think about a video game you've watched or played. The world feels enormous, but the system doesn't render every leaf on every distant tree at full detail all the time. It saves effort. It loads what matters where you are looking, where you are moving, where interaction is possible. Not because the world is fake, but because the experience is constructed in layers, efficiently, locally, on demand. Now, reality is not literally a game engine. That metaphor can be abused. But it points towards something genuinely unsettling in quantum physics. At the smallest scales, the act we casually call measuring isn't just a passive glance. It's an interaction that forces nature to answer a question in a specific way. In everyday life, you imagine properties sitting there, fully formed. An electron has a position, like a marble has a position. A photon has a path, like a thrown ball has a path. In quantum mechanics, what you often have instead is a spread of possibilities, a wave function that encodes probabilities. Before an interaction pins it down, the theory doesn't give you a single definite value for certain properties. It gives you a menu with weights. And then the menu closes. That closing, whatever it truly means, is where the pixels feeling comes from. Not pixels as tiny squares of space, but pixels as discrete outcomes. The world, when pressed for an answer, clicks into one of the allowed results. You don't get any value. You get one of the values that the quantum rules permit. So measurement isn't merely reading a hidden label. It can behave more like choosing which question is even meaningful to ask. Measure position, and you get position-like answers. Measure momentum, and you get momentum-like answers. Try to ask for both with perfect sharpness, and the universe refuses, not out of stubbornness, but because the structure of the theory doesn't allow those properties to be simultaneously carved into reality with infinite precision. This is why some physicists speak as if observation has teeth. Not because a human mind is magical, but because any measurement device, any interaction that leaves a record, entangles the system with the environment. The delicate quantum spread becomes correlated with countless degrees of freedom. The possibilities stop interfering like waves on a pond. The world begins to behave as if one story happened and the other stories faded into irrelevance. That last sentence is important, as if, because here is where the quiet controversy lives. Quantum mechanics is unbelievably accurate, yet it has multiple ways to interpret what the math is telling us. One view says there is a genuine collapse. Something physically happens when a measurement occurs, and one outcome becomes real while the others vanish. Another view says nothing collapses at the fundamental level. Everything evolves smoothly, and what we call collapse is really a bookkeeping update, a practical consequence of entanglement and decoherence. Another view says all outcomes exist, branching into separate histories that no longer touch. The math can support different stories about what is really going on underneath. And that uncertainty is where the lazy loaded sensation returns. Because from the inside a human life, inside a lab, inside a single timeline, reality arrives to us as a sequence of settled facts. We open the box and find one result, We check the detector and see one click. We look and the world is crisp. But quantum theory whispers that crispness may be the surface layer, the solidity might be the user interface. The definitive answer might be the moment the universe is forced to commit, locally, contextually, because an interaction demanded a record. If that's true, it doesn't make the world unreal. It makes it conditional in a way our intuition doesn't like. It suggests the universe is not obligated to supply a fully specified story everywhere at once, in the way classical thinking assumes. It supplies what is demanded by interactions, and the rest remains described by probabilities until it matters. And once you feel that, a colder question forms on its own. If outcomes become definite through deep correlations, if the universe locks in answers when the conditions are right, then how far back do those correlations reach? How much of what feels like choice and chance and freedom is actually woven into the fabric long before we notice the thread? Not as a panic, not as a prophecy, just as a thin, strange possibility, waiting quietly behind the interface. There's a certain kind of idea that doesn't scare you with explosions or monsters. It scares you with bookkeeping, with the possibility that the universe is so tightly accounted for, so perfectly stitched together, that even the questions you ask were always going to be asked. This idea is called superdeterminism, and it shows up in physics because of a very specific tension. Quantum mechanics seems to suggest that outcomes are not fully decided until a measurement happens. Meanwhile, our older instinct, the classical instinct, wants a world where properties are there the whole time, waiting to be revealed. So, we built a famous test for that instinct. In experiments inspired by Bell's theorem, you take two particles that share a deep quantum link. You separate them, you measure them, and you choose measurement settings in a way that's supposed to be independent, like flipping a switch at the last moment. If the universe behaves like a classical script, then the particles would need hidden instructions, pre-written answers, to coordinate their results. But Bell's result says, if the choices of measurement are truly free and independent, then no local hidden instruction set can reproduce what we see. That's the trapdoor. Superdeterminism doesn't argue with the math. It simply questions the assumption that the measurement choices were independent in the first place. It whispers something almost too calm to notice. What if the particles and the choice of settings were never separate facts? What if they were correlated from the beginning, not by a signal traveling between them, but by the shared history of the universe itself? In that picture, the coin flip that chooses the setting isn't really random in the deep sense. It is the end of a causal chain that goes back, through your hand, your brain, the lab, the planet, the star, the early universe, into the same cosmic ancestry that also produced the particles you're measuring. The particles don't need to send messages. They don't need spooky faster-than-light coordination. They simply knew what would be asked, because what would be asked was already woven into the same fabric of causes. It's a way of saving a certain kind of realism, a way of keeping the comfort of definite properties, a way of keeping the universe local and mechanical. But the price is immense, because once you accept superdeterminism, you accept that the freedom of choosing what to measure is not truly free in the deepest sense. It becomes another physical variable, another domino, already leaning in a particular direction. And that's why it feels cold. Not because it automatically destroys free will in your everyday life. You still feel choices. You still weigh options. You still learn. You still change. Life still behaves like a branching tree from the inside. But superdeterminism invites a different interpretation of that feeling. It suggests that the branching may be an appearance created by limited knowledge, by being embedded inside the system you're trying to describe, like a character inside a novel experiencing suspense, while the last page already exists. Now, to be fair, physicists don't adopt this idea casually. It has a reputation. One reason is that it can sound like an escape hatch. If every choice is secretly correlated with what it measures, then you can explain almost anything by saying, that correlation was always there. It can start to feel unfalsifiable, hard to test, hard to corner, hard to distinguish from a universe that simply has genuine quantum randomness. And many people consider that a serious problem. Science doesn't just need explanations. It needs explanations that could have failed. Still, the reason superdeterminism keeps returning, quietly, stubbornly, is that it offers something very tempting, a universe that behaves with strict causality all the way down. No randomness that is fundamental, no miracles hiding in the machinery, just deeper constraints we haven't learned to see. So, this is the shape of the idea. Not a prediction, not a prophecy, not a claim that your thoughts are fake, just a possible map of how reality might keep its accounts balanced. And if the map feels unsettling, that's okay. Some maps are meant to guide. Others are meant to remind you how vast the territory is, how many ways the same sky can be understood. Because even if the universe is written in advance, you are still the part of it that gets to read the lines, slowly, one at a time. Somewhere along the way, the spiral changes texture. It stops feeling like far-away theories about distant stars or exotic particles, and starts feeling like a set of quiet questions about what it even means for anything to be stable, to be known, to be real. So before we step deeper, let's hold the whole shape of what we've already traced, gently, without tightening around it. At the first layer, we look down at the most ordinary promise your life is built on. That the floor is solid, that the rules underneath you are settled, that reality is running on something permanent. And we let that promise wobble, just a little. We imagine the vacuum, not as empty space, but as a kind of background state, a resting position of the universe. The unsettling part wasn't drama. It was the possibility that the resting position could be temporary. Not temporary like a countdown timer, but temporary like a valley that isn't the deepest valley, stable for eons. Stable enough for everything you've ever touched, yet still, in principle, not the final word. Then we held another strange possibility in the same palm, that even matter itself might have a deeper, more stable arrangement, so stable that it would make our familiar atoms feel like a convenient phase, not the fundamental default. And we acknowledge the sanity checks, the reason scientists don't treat it like an imminent threat. The point wasn't to scare, the point was to loosen the grip of certainty, to admit that normal might be one local solution to deeper equations. And we lingered briefly on the quietest mystery of them all, the energy of empty space, the cosmic push we call dark energy, a label that fits our observations, without yet giving us the comfort of understanding. The universe expands, we measure it, we name the cause, and then we confess softly that naming is not the same as knowing. That was the ground layer, the sense that what feels solid may be stable by luck, by structure, by deep physics, but not necessarily by necessity. Then we lifted our eyes to the sky, and instead of asking, "Where is everyone?" like a joke, we asked it like a probability problem. We walked through the great filter as a shadow cast by the silence, an unsettling shape because it can fall behind us or ahead of us. If it's behind us, then life that can think and build might be rarer than we want to believe. If it's ahead of us, then civilizations may tend to break before they can become loud, lasting, and visible. Then we explored a colder interpretation of silence, not emptiness, but strategy. A universe where being detectable is not always an advantage. A dark forest where the safest move might be stillness, where the first sign of you might also be your last mistake. And we kept the humility intact. It's a model, not a law. A story we tell because it fits some game theory instincts, not a conclusion the cosmos has signed. After that, we followed the logic that doesn't require fear or hatred, only engineering, self-replicating machines, probes that copy themselves, spread exponentially, and turn exploration into something like an automated weather pattern. No villain required, just a system that, once started, keeps going because the math of replication is hard to put back into the bottle. And then, one step colder still, the idea that expansion could be the default behavior of successful life. Not because anyone is evil, but because selection rewards the civilizations that spread. And from inside a young, quiet pocket of the universe, it might look like emptiness, when it's really just timing. That was the sky layer, the sense that silence can have reasons, and those reasons don't always care about what we hope is true. Then, without changing the volume, we turned inward, toward the mind that's listening right now. We considered the possibility that perception is not a window, but a dashboard. That evolution might tune us for survival, not for truth. That what you experience as reality could be an interface, useful icons standing in for a deeper operating system you never directly see. And we let quantum theory press on that idea in its own peculiar way. The way measurements don't merely reveal, but seem to select, as if the universe does not owe you a fully rendered story everywhere at once. Not a literal simulation, not a game, just a structure where definite outcomes are born through interaction, through records, through the world becoming entangled with itself, until one storyline is the only one you can meaningfully talk about. Then we arrived at a thought that feels like cold math: superdeterminism. The possibility, controversial, difficult, not widely accepted as settled, that the free choices in our experiments might be correlated with the systems being measured, not by signals, but by shared history. A way to keep causality strict, by paying with a new kind of discomfort about independence and choice. So here we are. If the ground may be more fragile than it looks, and the sky may be quiet for reasons, and the mind may be seeing a useful interface rather than the final truth, then the next layer is almost inevitable. It's the layer where the question becomes less about what happens and more about why the universe has a direction at all. Why does time feel like it moves one way? Why does order seem to leak? Why do patterns, stars, bodies, thoughts, require constant conditions to remain patterns? This is where we begin talking about entropy, not as a scary word, but as a gentle accounting rule. The kind of rule that doesn't shout, but slowly, patiently shapes everything. There's a quiet rule humming underneath everything you've heard tonight. Not a villain, not a prophecy, just a tendency. You can feel it in small, ordinary ways, so ordinary we stop noticing it. A hot cup of coffee cools down. A drop of perfume spreads through a room. Ice melts. Smoke doesn't politely gather itself back into a candle. A shattered glass does not unshatter on a bored afternoon just to prove a point. We call this tendency entropy. And when people say entropy always increases, what they really mean is softer and stranger. In a closed system, the universe has more ways to be messy than neat, more ways to be spread out than tightly arranged. If you don't force order in, if you don't do work, things drift toward the states that are easiest to become. Not because the universe is cruel, because the universe is statistically patient. Picture a brand new deck of cards. It starts in a rare arrangement, ordered, grouped, pristine. Now shuffle it, once, twice, 10 times. You will not accidentally shuffle it into perfect order again. You could shuffle for the rest of your life and never see that original arrangement return. Not because it's impossible, because the number of disordered arrangements is so unimaginably larger than the ordered ones that the ordered ones might as well be a single grain of sand on an endless beach. Entropy is that beach. And here's where it turns from a physics word into something that presses gently on the edges of your thoughts. Entropy is the reason we can tell time. Not clocks exactly, not calendars. Time in the deeper sense. The feeling that the past is fixed and the future is open. The sense that before and after means something. Because if the laws of physics are mostly happy to run forward or backward, why does your life only run one way? Most microscopic laws don't care about direction. If you filmed two atoms colliding, then played it backward, the backward version would still look plausible. The basic equations don't scream, that's illegal. So, where does the arrow come from? It comes from entropy. Time feels like it has a direction because the universe is constantly moving from less probable arrangements to more probable ones. From concentrated energy to spread out energy, from structure to dispersion, from a narrow set of options to a wider one. It's like watching ink diffuse in water. The laws allow it to reverse in principle, but you never see it because reverse requires a miraculous coordination of countless particles, an orchestra of molecules all choosing at the same time to play the same note. Entropy is the reason they don't. So, when you look at the world and feel its forwardness, the way memories pile up behind you and possibilities stretch ahead, what you are really sensing is a flow of information, a record being written. Because entropy is not just about mess. In modern physics, it's deeply tied to the number of microscopic configurations that look the same from far away. It's tied to what you don't know about the details, even if you know the big picture. You can know the temperature of a room without knowing the exact positions of every molecule. That ignorance isn't a personal flaw. It's built into what it means to describe reality at a human scale. Entropy is the cost of zooming out. And there's a kind of eerie comfort in that, because it means the world you experience, solid surfaces, warm blankets, the hum of a fan, the heavy calm of nighttime, is not the full world. It's a stable summary, a compressed file. The deep details are there, underneath, but you live in the clean version that keeps you functional. Now, if you let this idea drift a little farther, it starts to touch the earlier spirals we've walked through. If the vacuum itself might be metastable, if the cosmos might be quiet for reasons, then entropy becomes the soft background music tying it together. Because entropy is also a story about energy. Energy can't be destroyed. That part is famous, but energy can become less and less useful. It can spread out into forms that are harder to gather and harder to aim. A battery is useful energy, organized energy. A warm room is energy too, but it's diluted into countless tiny motions. It's still there, but good luck pulling it back into a neat, concentrated package without paying a price. Entropy is why engines need fuel. It's why stars burn through their internal order, step by step, for billions of years. A star is a machine that takes concentrated nuclear potential and leaks it outward as light and heat. Beautiful, steady, irreversible. It's why life is possible at all. Because life is not a rebellion against entropy. Life is what entropy looks like when there's a powerful energy gradient, like a hot star shining into cold space. Living things keep themselves ordered by exporting disorder. You build a body by burning fuel. You maintain a mind by consuming energy. You create a thought by turning organized chemical energy into heat. You get to be you because the universe lets you borrow order for a while, so long as you pay it back with interest. That's the quiet tax. And if that sounds bleak, it doesn't have to. It's also tender, because it means your calm moments are not accidents. They are achievements, local islands of order, held gently in place by constant invisible work. The steady pumping of your heart, the chemistry in your cells, the stable star that keeps your planet warm. Even rest has a physics behind it. Now, here's the twist that often catches people. If entropy is always increasing, why does anything ever become more ordered? Why do crystals form? Why do planets gather? Why do galaxies appear instead of a smooth fog? Because entropy is a global rule, not a local curse. A system can become more ordered in one place if it increases disorder elsewhere. When water freezes into a crystal, the molecules become more ordered, but heat is released into the environment. The total entropy, including surroundings, still rises. When gravity pulls matter together into stars and galaxies, it looks like order. But gravitational systems are peculiar. Clumping under gravity can actually open up more ways to rearrange energy overall. As matter collapses, it heats up, radiates, stirs, and creates vast reservoirs of thermal motion. The universe can build breathtaking structure while still sliding, overall, toward the more probable states. So, the arrow of time doesn't mean everything becomes chaos tomorrow. It means the accounting always balances. Every neat pocket of reality is paid for with a larger spread of energy somewhere else. And if you're listening closely, you'll notice something haunting in that idea. The arrow of time might not be a fundamental law. It might be an initial condition, a fact about how the universe started. Because for entropy to increase, the universe must have begun in a relatively low entropy state, an extremely special arrangement. And that raises one of those questions that feels like it belongs to a different kind of science, or a different kind of story. Why was the early universe so ordered? Why wasn't it born already shuffled? Physicists can describe what happens next with remarkable precision, but the why of that beginning, the clean, low entropy starting line, still sits there like an unopened letter. And that letter matters because it's not just about galaxies. It's about memory. It's about identity. A memory is a physical record, a pattern in a brain, a trace in a notebook, a file on a drive. Records only form when entropy increases. To remember something is to create an irreversible mark, a footprint in sand, a ripple that doesn't perfectly reverse. Your sense of self is built out of those irreversible marks. You are, in a very real way, a creature made possible by the arrow. So, when entropy whispers that time has a direction, it's not only speaking about stars cooling and coffee cups losing heat. It's explaining why your life has a then and a now. Why the past feels heavy with facts, and the future feels light with maybes. And now, with that arrow in your pocket, soft, invisible, but steady, we can approach an even stranger question without getting lost. If time's direction comes from statistics, if order is borrowed, if records are physical, then what happens when the universe is old enough and quiet enough? That randomness itself can start to impersonate meaning. Because in a universe that runs long enough, even a whisper can assemble itself into a voice. Not because it's likely, because given enough time, likelihood stops being a shield. And that's where the next idea begins. Imagine a universe that lasts for a very, very long time. Not just billions of years, not just trillions, but so long that words like forever start to feel less like poetry and more like a parameter in an equation. When physicists talk about the far future, they sometimes picture a cosmos that becomes quiet and thin. Stars burn out, galaxies drift. The temperature of everything drops closer and closer to a uniform, sleepy baseline. In a picture like that, the universe doesn't end with a bang. It relaxes, it fades. And then comes a question that feels like it shouldn't belong in a serious scientific conversation. In a universe that is mostly empty, mostly calm, mostly uniform, could a mind still appear? Not a life form evolving on a planet, not a civilization building telescopes, something stranger, a single observer. A brain-like structure assembled by chance for a moment, out of the random jitter of matter and energy. This is what people mean by a Boltzmann brain. The name sounds playful, but the idea is unsettling in a very specific way. Not because it predicts a monster, not because it predicts doom, but because it pokes at the rules that tell us when a theory is healthy, and when it has wandered into a self-defeating corner. Here's the gentle setup. Entropy is the universe's quiet accounting system. It doesn't hate order, it simply makes order expensive. The more organized something is, an ice cube, a living cell, a library of memories, the more special it is compared to the countless messy arrangements that could have existed instead. That's why, left alone, hot coffee cools down. That's why rooms get dusty. That's why we have to keep putting effort into maintaining anything. Now, take that same logic and stretch it across the whole cosmos. If the universe lasts long enough, it will spend most of its life in states that are extremely high entropy, very uniform, very scrambled, very nothing in particular. And yet, even in a high entropy state, statistical fluctuations can happen. If you shake a box of letter tiles long enough, once in a great while, a few tiles might land in a pattern that looks meaningful. Not because the box wants it, not because it's guided, just because randomness, given unlimited tries, eventually stumbles onto rare patterns. In the same way, if the universe has essentially endless time, a rare low-entropy pattern could appear by accident, a swirl of particles here, a brief pocket of structure there. And the bold question is, if you wait long enough, is it more likely for a whole planet full of life to arise? Or for a single brain-like arrangement to pop into existence for a second, complete with a flood of thoughts? A brain doesn't need oceans and ecosystems. It doesn't need billions of years of evolution. It only needs the right arrangement of matter for long enough to have an experience. And if that experience includes memories, memories of a childhood, a sky, a history, a scientific education, then it might feel like it's part of a long story, even if it was only assembled moments ago. That is the eerie core of the Boltzmann brain scenario, an observer that wakes up with a full set of convincing memories, in a universe that is otherwise empty and silent. Now, here is where it turns from spooky to important, because physicists don't bring up Boltzmann brains to scare you. They bring them up as a warning light on the dashboard of a model. A good theory of the universe should make observers like us unsurprising, not miraculous, not rare to the point of absurdity. But some cosmological models, especially ones involving eternally lasting space, or certain ways of treating vacuum energy, or certain versions of inflation, can accidentally imply that random observers vastly outnumber evolved observers. And if that were true, then a strange conclusion would follow. Statistically, you should expect to be a Boltzmann brain. You should expect your memories to be unreliable, your measurements to be suspect, your sense of being embedded in a long, consistent world to be a temporary illusion. And that's the paradox. Because the moment you accept that conclusion, you undermine the entire practice that produced the model in the first place. Science depends on the idea that our observations are connected to a stable external reality, and that the past was real enough to leave reliable records. If a theory predicts that most observers are brief hallucinations with counterfeit histories, then it has turned the tools of reasoning against themselves. So, what do scientists do with this? They don't throw up their hands. They use it as a filter. Models that generate too many Boltzmann brains are treated with suspicion. Physicists look for mechanisms that prevent them, ways the universe might end before those timescales matter, or ways the vacuum behaves that avoid the problem, or ways probabilities should be defined, so the counting doesn't explode into nonsense. In that sense, Boltzmann brains function like a gentle test of sanity. Not a prophecy, a stress test. If a cosmological story accidentally implies that the most common kind of you is a lonely flash of awareness in the dark, then something about the story is probably missing a piece. And there's one more quiet comfort hidden inside this whole thought experiment. The fact that we can even notice the paradox is a kind of anchor. We live in a world with continuity, with shared history, with consistent physical laws that let us build clocks, store memories, and compare notes with one another. Our universe is not a perfect still pond. It's structured, dynamic, richly connected. Boltzmann brains are what you get when you take time to an extreme and forget to ask whether a theory still respects the basic requirements for doing science at all. So, the point isn't to make you doubt your own reality. It's to remind you that the best theories don't just sound clever. They remain livable. They leave room for real observers, in a real cosmos, with a real past behind them. Let that idea loosen its grip for a moment. You don't have to solve anything tonight. Just notice the simple weight of your body where it rests, the way the bed, the chair, the floor quietly holds you. If it helps, let your shoulders drop a fraction. Unclench your jaw. Let your tongue rest. Take one slow breath in and let it go a little longer than you took it in. Whatever strange possibilities exist at the far edges of physics, they don't need you right now. Your mind can set them down gently, like a book closed halfway, save for another day. And for the next few moments, you can return to something smaller and steadier. This room, this breath, this quiet present, as we drift forward. Some endings don't arrive like a crash. They arrive like weather, slow, indifferent, almost too large to notice from inside a single lifetime. When cosmologists talk about the end of the universe, they aren't picturing a dramatic curtain falling. They're following a few quiet trends: expansion, gravity, temperature, energy, out to their farthest consequences. And the eerie part is not that these possibilities exist, but that they sound, in their own way, almost natural, like the universe simply continuing to do what it has been doing all along. One possibility is sometimes called the Big Rip. It's a story about acceleration, about the space between things stretching faster and faster, as if the universe keeps pressing harder on the gas pedal. If that push were strong enough, gravity would slowly lose its grip. First, the largest structures, clusters of galaxies, would stop holding together. Then galaxies, then star systems. The distance between once bound objects would become too eager, too insistent, for gravity to stitch back up. And if you try to picture it, don't picture violence. Picture a fabric being pulled, gently at first, then more persistently, until seams that held for billions of years begin to give. The rip in this scenario isn't a sound you hear. It's separation becoming the dominant rule. But it's also important to say, this is not a prediction carved into stone. It depends on the detailed behavior of dark energy, something we can name more easily than we can explain. The Big Rip is one way the math can go, not the only way it must. Another possibility feels quieter still. Heat death. The long settling of everything into sameness. Heat death doesn't mean the universe suddenly goes cold, like a switch is flipped. It means differences fade, and differences are what power everything interesting. Stars shine because there's a gradient between a hot core and cooler space. Life persists because energy flows from high to low. Even thoughts are little cascades of organized change. If the universe continues expanding, matter thins out. Stars burn through their fuel. New stars become rarer. The bright, busy era of galaxies becomes an old memory written into light that keeps traveling long after the sources have dimmed. Over immense time, energy spreads more evenly. Temperature differences smooth out. The cosmos approaches a state of maximum entropy. Not chaos in the everyday sense, but a tired equilibrium where there's no downhill left for energy to roll. In that far future, there can still be particles, still be space, still be time in some sense. But the engine of change becomes hard to start. The universe doesn't end with a bang. It ends with a slow exhale that never quite finishes. And then there is a third ending that feels less like weather, and more like a hidden trapdoor in the floorboards, vacuum decay or a vacuum shift. This one begins with a subtle thought. What we call empty space isn't truly empty. It's a state, a background configuration of fields. And in physics, a state can be stable, or only stable for a while. If our vacuum is not the deepest possible state, if it is metastable, then it could in principle transition to a lower energy configuration. The unsettling part is that such a transition wouldn't be a local disturbance like a storm. It would be a change in the rules themselves. The values of fundamental constants could differ. The behavior of particles could differ. Chemistry, as we know it, might not even be something that can happen. In some versions of the story, the transition would begin as a tiny bubble, smaller than an atom perhaps, then expand outward at nearly the speed of light. And because nothing can outrun that boundary, there would be no warning that arrives in time. But even here, the most honest tone is not terror, it's humility. We don't know whether our vacuum is truly metastable. We don't know whether such a decay is physically realized in our universe. We don't have a clock for it. This is a theoretical door the equations allow, not a scheduled appointment. So, you can hold these endings the way you might hold distant thunder, real enough to respect, far enough to remain calm. Because there's another truth that matters just as much. Every one of these scenarios lives on time scales so vast, they barely fit into language. They aren't bedtime fears. They're cosmic possibilities, maps drawn at the edge of what we can compute. And right now, inside the small circle of your own night, the universe is doing what it has always done near you. Gravity still gathers. Atoms still keep their quiet agreements. The air still rests against your skin. Whatever the far future becomes, this present moment is steady, real enough, gentle enough. It helps to remember what these ideas really are. They are not alarms. They are not predictions. They are not secret messages about what will happen to you or to this world tomorrow. They're closer to maps, carefully drawn sketches at the edge of what our best equations can reach. When scientists imagine a big rip, or a slow heat death, or a shift in the vacuum itself, they're doing something very human. They're taking the rules we've measured here, through small laboratories and distant telescopes, and asking what those rules might imply if we let them run forward for an unimaginably long time. And maps can feel eerie, especially when they show places we've never been. But a map doesn't force the journey. It doesn't demand fear. It only describes the terrain as best as we can see it from far away. And sometimes the most valuable thing a map can do is shrink fear into perspective, not by denying the unknown, just by giving it a shape the mind can hold, without panic. Because the deeper lesson underneath every terrifying theory is strangely gentle. Reality is vast, and our certainty is local. We live inside a small pocket of stability, a thin layer of warmth, pressure, chemistry, memory, and light. That pocket has lasted long enough to grow oceans and forests and cities, and you, listening right now. Whatever the far future becomes, this present moment is part of the universe's real story too. So, if these possibilities leave a chill in the imagination, let that chill drift outward, back into the cosmos where it belongs. Let the mind stop gripping the edge of the unknown. Tonight, you don't need prophecies. You only need a softer relationship with uncertainty. A map, not an alarm. And now, gently, we return to what's nearest. Not the edge of the universe, not the far future, just this small, ordinary pocket of night, where you are. Whatever reality truly is, whether it's deeper than we can sense, stranger than we can picture, or written in rules we haven't found yet, this moment is still allowed to be simple. A quiet room, a steady breath, a body that knows how to rest. And if your mind is still holding one of those ideas, you don't have to push it away. Just set it down, like something fragile and interesting, something you can pick up again in daylight. The universe can keep its mysteries a little longer. It has patience, and so do you. Thank you for spending this time with me, here on the Quantum Slumber. If you'd like more nights like this, more calm science, more gentle questions, more soft perspective, you're always welcome to come back. And if you feel like it, you can leave a small note below about where you're listening from. I love seeing how far this quiet reaches. But for now, let the questions fade into the background. Let the dark be kind. Good night.